We talked, actually by now it's been a long time ago, about the derivative of the natural log of x, and it was 1 over x. We also talked about the derivative of the natural log of the absolute value of x, and we said that was also 1 over x, just different domain, but same idea. What we need to do today is talk about, well, one of the first things we're going to do today is talk about integration with the natural logarithm. We are not going to talk about how to integrate the natural log of x. We may look at that at the very end of the year, but integrating the natural log of x means what has a derivative of the natural log. We don't really know that. What we're going to focus on instead, let me get this right. Okay, what we're going to focus on instead is finding the integral of 1 over x dx, which we can't do with the power rule, because you know, add 1 to the power, you get 0, divide by the new power 0, not going to work. But this is like asking what has a derivative of 1 over x. Natural log of x. And actually, though, that's only valid if x is positive. If I want to make this valid over almost the entire real number line, I can say the most general answer is the natural log of the absolute value of x. That's the most general solution. Well, actually, hold on, I'm not totally done. What am I missing? We're doing integrals plus c. The integral of 1 over x dx is the natural log of the absolute value of x plus a constant. And actually, I want to do this in one other way. We can also view this, though, as just a special case of the power rule. What is the integral of x to the n dx? Well, usually, it's going to be x to the n plus 1 over n plus 1 plus a constant, as long as our power isn't negative 1. We can't use the power rule if the power is negative 1. What do we do if the power is negative 1? Well, that's where we get our new natural log of the absolute value of x plus a constant from. Which means now, technically, we can handle any sort of power. We were pretty good before, but now we've got the complete story. As we move forward with stuff today, this is what I mentioned at the end of class yesterday and confused some people because I didn't actually then teach you anything new. Today is going to be about integration. We're not talking about the product rule, the quotient rule, the chain rule, those things. We're talking about integration. And our one big trick for integration is mostly U substitution. That's what we need to focus on today, not our derivative rules. But let's get started with something like this. Let's take a look at the integral of 10 over x dx. Is the 10 helpful for you? What can we do with it? When you say take it out a 10 or take out a 1/10? Say that again? Take out a 10. I'm not doing U substitution or anything here trying to make things work. It is a constant. I'm just going to move it out front. And I'm going to say 10 times the integral of 1 over x dx. Do you know how to integrate 1 over x dx? What is it? The natural log of the absolute value of x plus c. Okay, so 10 times the natural log of the absolute value of x plus a constant, which is absolutely fine for an answer. However, if this was a multiple choice question on the AP exam, there may be another way they would write it instead of that. We also need to remember that with these natural logs, we have some properties that we can use to write it in a different form. What am I talking about here? Tanush. That 10, I can turn into a power. I can say this is the natural log of the absolute value of x to the 10th plus c. And actually, do I even need absolute value bars anymore? Did I need them over here? X could be positive, x could be negative. Why are you saying I don't need them? X to the 10th is always something positive, so really, we could just simplify this to the natural log of x to the 10th plus a constant. And part of what we're going to look at today is how we can write answers in different forms and just realize they're all valid forms. I would take any. I'm not crazy about the middle one, only because we don't need the bars there, but I would take any of those. Yeah, just to show it's truly all inside there, I guess. Okay. Let's take a look at the integral of 1 over 2x plus 3 dx. Is this exactly one of our integration formulas, the way it's written? It's not. You really know, well, you know two tricks, I guess. You know algebra that we can use to rewrite things. I don't see any algebra that can be used here. What's the other big trick for integrals? I've already said it. U substitution. If we try U substitution here, what could we try making U? So you mean the entire denominator? Okay, let's try it. If we say U is the entire denominator, 2x plus 3, du then would be 2 dx, which I feel like I can make work. We've got the integral. I'm just going to rewrite the problem so you can see how I stick the u and du stuff in here. What do you need inside? 2. And then you got your 2 dx. That's all good. What else? 1/2 on the outside. And we can turn this problem into 1/2 times the integral of du over u. How about you try to finish this? You should know how to integrate du over u, or 1 over u du, just another way of writing it. And then when you're done, because it's not a definite integral, it's just an antiderivative, you'll replace the u with what it stood for. How about 1/2 times the natural log of the absolute value of 2x plus 3? Do I need the bars? Yeah, because that thing could be positive, could be negative. If you feel, I'm not going to do this, but if you felt like it, what else could happen? Could become a square root. We'd still need the bars, because stuff under the square root is not necessarily positive, but the bars will keep our domain. Ferris. Yeah, what's the integral? Well, isn't du over u like 1 over u? Du, just another way of writing it? This thing over here, isn't this just like 1/2 times the integral of 1 over u du? They mean the same thing. And then that's our new rule. Lady.
Can't you just skip the substitution and just put whatever's under inside the bars?
Then you wouldn't have gotten your 1/2 up front. And if you try to check things and find the derivative, chain rule will lead you to a different thing than what you started from. So no, we do need our u substitution. We didn't need that in the first one, but here absolutely we do. Okay, next one. Let's try the integral of 3x squared plus 1 over x cubed plus x dx. And we're going to draw a line over there, new problem. The trick is almost always u substitution, and we've got to find a u whose derivative more or less shows up. Oh, the bottom, like everything else we're doing today. X cubed plus x. Du then? Oh, that's kind of nice and convenient. Go finish it. By the way, if I gave you 3x squared plus 2 up top, you wouldn't be able to handle this. I can only still give you very specific types of problems, or things are not going to work. Natural log of the absolute value of x cubed plus x plus c. You can, but that'll take longer than actually just doing. I mean, you can always do that with integrals, but that's not the best way to go about doing things. Anything here? Okay, I've got a few more like this that I want to look at, and then we'll look at a few variations on this idea. So, let's try the integral of the cosecant squared of x over the cotangent of x dx. You know what? I think I'm just going to give you a chance to look at this, think about things, and see what you could do with this. The integral of the cosecant squared of x over the cotangent of x dx. See what you can make of this. Also keep in mind, like, what we're doing today. Thoughts on how to start? Cosecant squared x, the u, its derivative then is 2 cosecant x times negative cosecant x cotangent. It's gonna... Should we hurry? Make u the denominator. Well, if we try that, remember we want to pick a u whose derivative should more or less show up. What's the derivative of u, of cotangent of x? Negative cosecant x dx, which is more or less what we have there. So yeah, we can make this, negative not cosecant x, negative cosecant squared x. So, again, I'll just rewrite things so I can kind of show the process here. I think you should be sticking a negative inside and a negative outside, because then our negative cosecant squared x dx becomes our du. This is negative the integral of du over u. And if you haven't already finished, go finish that thing. Bless you. Negative the natural log of the absolute value of u plus a constant. So I think negative the natural log of the absolute value of the cotangent of x plus c. Cotangent could give you a positive or negative answer, so yeah, we will need the bars there. In general, I'd say better to err on the side of including them if you don't need them. I'd give you credit for that. Versus not including them when you do need them, I would take off for that. Okay, next. Anything there? Okay, what about, okay, this will be strange. 1 over x times the natural log of x dx. What's your problem? What's the integral of the natural log of x? Whoa, 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 whoa. That's the derivative. What's the integral of the natural log of x? No, no, no. That's the integral of 1 over x. What was that, Plady? We don't know. Well, that would be nice. Make you what?
Oh, and its derivative is...
Well, no, the derivative of 1 over x is negative 1 over x squared.
So
Keep going.
You the invert, the natural log.
Let's try that. You don't know how to integrate the natural log, which means if it's going to be in a problem somewhere, maybe that will be part of our u, and that will just kind of get taken care of. Oh my gosh. Okay, so let's say u is the natural log of x. Its derivative is what? Charlotte, what were you saying a moment ago? Oh, so you mean like we already have all those pieces there? This is going to become the integral of, looks like 1 over u du. I'm just going to keep going. I'm not going to answer that yet. Finish it. It will look a little strange when you're done. That's okay. Two pairs or two bars? No. Because the original U didn't have the bars in there. Natural log of the absolute value of U plus a constant initially. Natural log of the absolute value of, well, we're sticking a natural log inside of a natural log. That's allowed. We can do f of g of x or whatever, or f of x, or that's all we're doing here. One more. You're going to do it on your own. Then I'll answer your question, Sonali. I'd like you to go do the integral of 1 over, let's put a square root in here this time, square root of 2x minus 1 dx. Go do it. And of course you're thinking, what letter? U, of course. Lady, what did you just say? You don't need to do the thing.
It's the natural log. Just do it normal.
What do you think about what she just said? We don't need natural logs?
Because it's not -1.
Yeah, I just did it normally.
Going back to the beginning of our notes, I gave you that new rule, but then I also said that this is really a special case of the power rule. If our power is -1, that's where we're getting natural logs. If the power is anything else, no, it's normal power rule stuff. That's what I wanted you to see here. Everything has been natural logs because that's what the section is. But in general, no. Only if it's 1 over U, 1 over anything else, well, we use those rules for. So what are you really doing here? You should be actually doing 1/2 times the integral of U to the -1/2 du, and you're using our regular power rule, not our new special case where the power is -1. Don't get complacent and just assume everything's going to have a natural log in it, because it won't. Oh, that's actually kind of nice. Times 1/2 divided by 1/2. Maybe square root of 2x minus 1 plus a constant. Just because there's a denominator does not mean you're going to get natural logs. Questions? Okay. I'm going to wait a moment. And then we'll do a few variations. Oh, they can hear everything. Yes. Are we ready to go? Okay. So a few variations. Do I just do this? No, I'm going to give you a title for this. Okay. So sometimes we need to use algebra to do some rewriting stuff. We've already seen how we can FOIL, separate the fraction, all that. Well, there's something else that will sometimes be useful, and this goes back to something you learned in Algebra 2 that starts with the word long and ends in the word division. Polynomial long division. You learned long division in like 3rd grade. That is not called long division. That is called synthetic division. And we'll see many cases where that's not going to work and we have to use long division. We'll review how long division works. Now, we're going to, hold on. Okay, first of all, this method is going to be used basically from here on out anytime we try integrating a rational function where the degree of the numerator is greater than or equal to the degree of the denominator. To integrate a rational function where the degree of the numerator, I'm just going to say NUM, is greater than or equal to the degree of the denominator. We are first going to use long division to rewrite our problem in a better form. First, use long division to rewrite the problem in a better form. And what are we doing? Oh, we'll do this. Problem, yes. And for our first example, we're going to take a look at the integral of x squared plus x plus 1 divided by x plus 1. Don't do anything yet, just copy down when we use this and copy down the problem. For starters, do you see why this is in the right form for us to use long division? Because the degree of the numerator, if you try making u like the numerator, well, then du is 2x plus 1, which is not the denominator, plus you can never really have a du in your denominator anyhow. If you make u the denominator, there's all sorts of other pieces up top that don't get taken care of. We can rewrite this problem using long division. Yes, I realize this one could also be done with synthetic division, but I do want to review the long division with this so I can show you one in a moment where synthetic division won't work, and we need to use this long division method. So, I'm going to start by writing x plus 1 outside my division symbol, and inside my division symbol, I'm going to say x squared plus x plus 1. There are 4 steps. We divide, we multiply, we subtract, we bring down and start over. We're going to start by dividing. We divide the leading term inside by the leading term outside. X squared divided by x. What is it? X. That's your first division answer. I'm going to write that above the x term. I'm going to kind of line up like terms here. I've divided. Now I multiply. I'm going to multiply x by everything out front, and I'm going to get x squared plus x. I've divided. I've multiplied. I'm going to stick some parentheses in there, and I'm going to subtract. Everything canceled except the 1. Can you do this again? So what's the 1? It's a remainder, and we're going to write it as 1 over x plus 1. Here's the point. Division is just another way of rewriting the problem. This thing that I gave you has the same meaning as x plus 1 over x plus 1. If you go and you graph this versus you graph that, the graphs will be the same. They're the same function, just written in a different form. Now, I feel like this part, the 1 over x plus 1, needs a u substitution. Does the x need a u substitution? We've seen problems like this before where part will, part won't. Okay, so let's go and write this as 2 separate integrals. The integral of x dx plus the integral of 1 over x plus 1 dx. Do a u substitution. You know what? See if you can finish this. Do a u substitution for that second piece, and then you can integrate. You can just do integration right away on that first piece. Let's see what we can get. You look a little confused. Okay. That's a really nice U substitution over there. Try that again. Oh, how about that? Not too bad. The whole point of long division is just to write it in a different form that we can then handle. Probably one part will just be a straight integration, the other part will be a U substitution. Let me give you one more that's a little bit tougher, and you'll have to use long division. You couldn't have used synthetic on this next one. And then we'll look at some other variations. Can you raise your hand if you need another moment with what's on the screen? And of course, if you're raising your hand at home, just push the pause button. Okay, next. Let's try, where is it? Let's try this one. Let's try the integral of 2x cubed plus 5x squared minus 10x minus, nope, hold on. This has got to be perfect or things won't work. Plus 4 all over x squared plus 4x dx. See what you can do. Why is long division necessary? You're looking at the degree. Degree of 3, degree of 2. The degree of the numerator is greater than or equal to the degree of the denominator. Need long division. Okay, go divide, and then see if you can finish the whole thing off. It will have a messy denominator, but it's actually a very good thing as far as your integration goes. I think, assuming I wrote the problem correctly. I think I'm done. Okay, and once you're done with your division, see if you got what I have. Straightforward, straightforward, use substitution. And I think you see why I had to make it come up perfectly. If not, you wouldn't be able to handle this with a use substitution. Bless you. The book isn't great with these types of problems, so the homework's going to be book work plus a worksheet. You'll have a few of these on a worksheet. And this is not going away anytime from here till the end of the year, no matter what topic we're looking at. If we see the degree of the numerator is greater than or equal to the denominator, we'll start by doing long division. Then maybe different things will happen based on what the result ends up being, but that's always our idea.
For when you separate the integrals,
Yep.
do you like solve the 2x minus 3 while you're still doing the
Yeah, I just decided why don't I integrate all at the same time, but there's no reason you couldn't integrate this first, and that's all fine. Are you still making notes, Ferris? Okay. So I have two more things we're going to look at in a moment. We need to do some definite integrals, and then some stuff with trig. Yes, we have to. Okay, next. I've got two definite integrals we're going to take a look at. Definite integrals. Find the area under a curve. First example. Integral from 2 to 3 of x over x squared plus 1 dx. What do you have to do? Thank you. Use substitution. What's u? What's du? 2x dx. Okay, so I'm going to go rewrite things. I've got the integral from 2 to 3 of x squared plus 1 dx. I assume you're about to stick a 2 inside and a 1/2 outside. Okay. So 1/2 times the integral of du over u. Aha! So, I need to deal with the numbers, and no, I should not have 2 and 3 because those are x values. Just like everything else we've done before with our definite integrals with u substitution, we've got to change those limits. Okay, well, x equals 2 becomes u equals what? 5. 2 squared plus 1 is 5. When x is 3, u becomes 10. Okay. So I'm really integrating this from 5 to 10. And maybe we'll just keep going together with this one. This is 1/2 times, okay, let's do the antiderivative. Antiderivative of 1 over u du? Natural log, the absolute value, okay, all that stuff. Do I now replace the u with x squared plus 1?
No.
Not with definite integrals. That was the point of me changing the limits. They're now u values. I'm going to plug them in. 1/2 times the natural log. I don't need bars around the 10, nor do I need bars around the 5, and we'll get this.
That's it.
However, when you do these problems, I do not want multiple natural logs in your answer. I want a single natural log. How do you subtract those things? You divide the stuff inside. So this is 1/2 times the natural log of 10/5. Or how about 1/2 times the natural log of 2? And I'd be okay with that. Or square root of 2. We could say natural log of the square root of 2 because that 1/2 can become a power. By the way, I hope you noticed I didn't include a plus c. Never plus c is with the definite integrals. Doesn't make sense to say the area is 5. Plus a constant. That means the area could be anything.
If it was a plus sign, you'd multiply.
Plus you'd multiply, exactly. And multiple things, anything positive goes up top, anything negative goes in the bottom of a fraction. Okay, one more definite integral. The integral from 1 to 4 of x minus 2 over x plus 1 dx. No. No, your answer would be the natural log of the square root of 2. Wait, hold on. Say. Why would you say long division? Oh, right. We didn't really see an or equal to one, but yeah. How are we going to deal with this? By doing some long division. So how about you just stop and take a moment, do your long division, and then we'll return back to the integral, because there is still some weird stuff that's going to happen here anyhow. Go divide. It should go very, very quickly, that division. Long division, because the degree of the numerator is greater than or equal to degree of the denominator. One minus 3 over x plus 1. How do you handle this? Aha. Straightforward one over here. U substitution over here. We need to do two separate. I think we're getting used to the idea of dealing with them in different ways. Is that 3 helping anything, by the way, from the numerator of the second one? So I can just move it out front as a 3 or as a 1/3. Not doing U substitution stuff, I'm just doing my constant multiplier rule. So I'm going to get this. See if you can finish this one. There are actually a couple ways you can integrate the beginning. Second one, though, is going to require U substitution and for you to change your limits of integration. There will be a log in your answer plus some other stuff. Got the integral of du over u from 2 to 5 for the second piece. How are you integrating 1 dx? There's 2 ways you can do it. Okay, I think the easiest way is realizing it's just a horizontal line. We're doing a rectangle thing, height of 1 going from 1 to 4. You could also use... Say that again? It will be 3, or you could use the first fundamental theorem of calculus. What's the integral of 1? You could say x from 1 to 4, although I think the geometry way would get you there a little bit quicker. The other one, we're going to get 3 times the natural log of the absolute value of u. Dealing with this between 2 and 5. This is 4 minus 1, minus 3 times natural log. I don't need the bars here because these are positive numbers. Oh, okay. 3 minus 3 times the natural log of 5 halves. Anyone want to do anything else for fun? Really? Yeah, what is it? 125 over 8. Yeah, we could cube both parts. That was kind of fun. Be able to convert between different forms. That's all I need you to be able to do. And realize that when you check your answers to the homework, you might be right, even though it doesn't look like the answer, if you could convert it to another form. Anything with these? Last thing we're going to deal with. I have been waiting for this for a long time. Trig integrals. What's the integral of the sine of x dx? This is not a trick question. Negative cosine x plus c, okay. And what's the integral of the cosine of x dx? Again, not a trick question. Sine x plus c. Okay. I'm really just including these here to make our list complete. The integral of the tangent of x dx. We put this in our notes before. We said not yet. Guess what? It's yet. Oh, you already have an idea, Rebecca. What are you thinking? Tan x is what? Okay. So Rebecca's saying we can write tan x as sine x over cosine x. Well, we certainly could have handled that before. U substitution. And what is u? If we made u sine x, du would be cosine x, but we can't have a du in the denominator. So u has got to be cosine x. Okay. Which makes du negative sine x dx. So to make this work, we can, I'm just going to rewrite it so we can see the process. Sine x over cosine x dx. We need a negative in, a negative out. Negative the integral of 1 over u du, or du over u. Negative the natural log of the absolute value of u, plus a constant. Negative the natural log of the absolute value of the cosine of x plus c. Moving forward, yes. Because in a moment, I'm going to ask you what's the integral of the tangent of 3x or something. We're not going to go through the derivation. We're just going to say, oh, we're going to make u the thing inside, and I now know how to integrate the tangent of x. So what is the integral of the tangent of x dx? It's the negative of the natural log of the absolute value of the cosine of x plus c. That is a new formula that, yes, we will need to know. However, there's another form we could write it in, and you do need to be able to at least recognize the two different forms, so I should show you the other form. This negative is like a negative 1 up front. I can make that a power inside here. What's cosine x in parentheses to the negative 1? 1 over cosine x, which is what? Another way we could write this is the natural log of the absolute value of the secant of x plus c. The first one's easier because it's a cosine, but the second one's easier because it's positive. Doesn't really matter, but you will need to know both. And if I just ask you what is the integral of the tan x and you give me one answer, that's totally fine. But be able to recognize that they're both valid. I am not going to go through the derivation for the integral of the cotangent of x dx. It's going to work the exact same way. You're going to say cosine x over sine x. You'll figure things out. I feel like I've been making comments all year long about trig, how all the trig things, derivatives, integrals, whatever, they all kind of come in pairs. Okay? So if we try to figure out the equivalent of the negative, the natural log of the absolute value of the cosine of x, do you think the integral of the cotangent, if we're looking at the first version of this, will be positive or negative?
Positive.
If one's negative, the other's positive, okay, so it's going to be positive. Then I'm going to have a natural log. Instead of a cosine, what do you think I might have? A sine. The integral of the cotangent of x dx is the natural log of the absolute value of the sine of x. There is an alternate form. It is rarely used, but I should include it. Do you think the alternate form is positive or negative?
Negative.
The negative of the natural log of the absolute value. Instead of a secant, what do you think? You're not really going to have 6 things to memorize. You're really going to have like 3 things to memorize, and you can use logic to get the other one. And there we go. You know what I think we should do? I think we should learn how to integrate the secant of x. Well, you're wrong. Okay. The integral of the secant of x dx. This is not as obvious. Not that the last one was obvious, but I think because you were thinking of what we were doing today and sines and cosines, and oh, then we can do a u in the denominator and get 1 over u. This is 1 over the cosine of x, so u is cosine x, its derivative doesn't show up, that's not going to work. There's a fancy little trick we can do that there's no way we would have just come up with. But watch what we can do here. I can say that this is the integral of the secant of x times, I'm going to multiply this by the secant of x plus the tangent of x over the secant of x plus the tangent of x dx. Forget asking why this is important. Do you see why I'm allowed to do that? Always allowed to multiply by 1, even if it's variable things, whatever. This doesn't look any better. Take a moment, distribute the secant x to the numerator. This becomes the integral of secant x times secant x, so secant squared x,